Last time we started section 5.1, the natural logarithmic function with differentiation, and we had left off on talking about the logarithm's derivative when you have an absolute value with the x on the natural log, the natural log of the absolute value of x. The derivative ends up just being 1 over x as well, and we had done this example. And when we did this example, we talked about the fact that it really mattered that sine of x had to be in absolute values. Does anybody remember what we said was the reason why?
Because it goes from like -1 to 1, so then it restricts that.
Right. The range of sine is from -1 to 1, and the natural log's input values must be greater than 0. So at the very least, we don't want the negatives, and we can eliminate those pretty quickly by putting some absolute value signs on them. We do still have issues, of course, if we try to take it at the zeros, right, at the x-intercepts themselves. So that doesn't eliminate all the problems, but it eliminates quite a lot of them. All right, let's take a look at another example. We have f of x equals 3x squared minus the natural log of x. We're given the point 1, 3, and this one actually asks us to find an equation of a tangent line through the point. Okay, so anytime you see the phrase equation of the tangent line, what are you going to be doing? Derivatives, right? Because in order to get a tangent line, in order to get a line at all, you need a slope and you need a y-intercept, or you need a slope and a point at the very least. So we have a point, that's good, we're given the point 1, 3, but we don't have a slope yet. So in order to get a slope, we need the derivative. So somebody tell me what you would get for the derivative of 3x squared minus the natural log of x.
-1 over x.
Okay, just a sec. All right, so what is the derivative of this one?
6x minus 1 over x.
Good. Does everybody have that okay? Yeah? All right, so now that I have the derivative, what do I need to do with the derivative in order to find slope? Right. This is the slope in general everywhere, but we actually want to find it specifically at the x value we were given, which was the x value of 1. So we have 6 times 1 minus 1 over 1, which gives me 5. So my slope is 5. And sometime way, way, way back in the far past, you learned a point-slope form of a line, right? That's the slope-intercept form, which you can use for this too. But point-slope form is a little bit more convenient.
Y minus y1 equals.
Good. So it's just a little bit more direct to use the equation with the points actually written in there. So this would be y minus the y value that was given, which was 3. The slope we just found was 5, and then we had x minus the x value given, which was 1. All right, so if we clean up and they simplify this, we get y equals 5x, and then we'd have 5 times -1 would be -5, plus the 3 on the other side would make it -2. Okay. There's nothing really different about that than what you've done in Calc 1, except that you had the natural log in there when you took the derivative. Okay. Any questions? All right, the next thing I want you to do is grab your calculator. We're going to use a calculator to graph the equation and the tangent line. So in part, what I wanted to use this problem for is a reminder, because some of you have taken 3 months or more off of Calc 1, right? And so it would probably be a good idea to remind ourselves how we go about doing all the parts of one of these problems, even though most of it is, in fact, review. All right, so go ahead and put the original equation in your calculator. And then in y2, go ahead and write the derivative equation that we just got, the tangent line. Yeah, not the derivative equation, the tangent line is what I meant to say. And then just make your window the standard 10 by 10 window. Okay, so My window is a little bit tight, maybe yours is too. It looks like if we zoom in, we might get a better picture, so I'm going to zoom in. I'm also going to zoom in on that. Oh, well, that's pretty good. And so my graph is up here, it looks like, in the top right corner, quadrant 1. That's not bad. All right, so we've got our parabola-ish shape right here, and we've got our tangent line, and it should appear, if you traced over to it, that they have the same x and y coordinate value at the point 1, 3, right? And in fact, if you wanted to, you could actually put in, let's see where it is again. I think it's underneath calc, so if you do second trace, and it says value, if you hit that button and you put in the value, in fact, you know what, let's do the table, that'll be even better. Let me go into the table. And if your table does not allow you to delete the way that I just did mine, let me know. Now's the time to ask, and we'll switch it. Okay, so we should be able to put in the x value of 1, and they should both say 3, because that's their point of tangency, right? Okay, so that's one of our confirmations that we did the problem right. We found the tangent line, at least in this regard, it's that part of it checks out. Okay.
How did you clear yours?
Did yours not clear?
How did you clear it?
Okay, you just hit delete, and if it doesn't, then it's just not set up yet to do that. So we'll set it up. Just a second. Table set. First one is here, mass. Did anybody else's not allow them to plug a value in? Okay. If you don't have your calculator with you, and that's something you have happen later, the way you change it is underneath table set right here. What you need is you need that first table set to say ask on the first line. So it allows you to actually plug in your own values that you care about in your table. That's how you change that. All right, so you ended up with a curve and a line touching it. So it should have looked something like this sort of lopsided looking parabola, right? And it had a tangent line on there. Something like that. And the point of tangency, like we mentioned, is actually this point at 1, 3. All right, another cool feature of your calculator to remind you of again is to use the Derive feature, or use the Derive feature on your calculator to confirm. So to use the Derive feature on your calculator, I'd like to remind you how to do that as well. So go back to the regular screen on your calculator. Okay, so just the regular computational screen. And underneath the math button, so click on math. There's an option, if we go far enough down, it's option number A that says in Derive, or in Derive, this one. Select that one. Now, this is sort of the texty type looking one. If yours has pretty math type, it looks different. I can show somebody's with that too. Does somebody have a pretty math type one? I'll borrow these. Okay, so if you have the pretty math type, it actually shows up with a derivative notation like this. Hang on. Is it going to show up or not? Oh, man. Yeah, okay. I'll just draw it on the board.
Do you want mine?
Yeah, it hurts
Do you think? Okay, let's give it a shot.
the
It's too fun, huh? All right, that'll work. Okay, so on this one, you're going to do the same notation. You're just going to do it in different spots. The first thing you have to tell it is what equation it wants. Now, if you've already put the equation in y1, which we have, we don't need to enter the equation in it again. You can, but you don't need to. So the way that you do that is you hit the vars button, and it works the same over here. You go over to yvars. It's a function, so we're going to select number 1 function, and the function is saved inside of the y1 graph feature. Okay? So that's the first thing I hit here. I should have moved this one over, so on top of this box is where I want it to say y1. So I'm going to go through that again. Vars, yvars function y1. All right, the next thing I have to say in the text type one is I need to put a comma, and I need to tell what the variable is. Well, the variable is x. It's the letter that was used. And we have to do the same thing over here, the d dx. So that's where the x goes there for the same reason. And then the last thing that we need to do is we need to tell it the evaluation at what point. So on my calculator, I'm going to put a comma and a 1 because it was evaluating at x equal to 1. Over here, where it says x equals down in the little right-hand corner, you're going to put a 1 here. And when we're going to hit enter, and they should both tell us the value. Hang on, what did I do? Did I have them saved as my one? Oh, they're approximating because it's numerical features. They're both giving us 5. They're just giving us a numerically estimated slope. They're not using calculus. They're using numerical methods to estimate. So this number, 4.9 with all the 9s, is the same as the number 5 that we were getting because we got a slope of 5, right? Yeah. So we're good. So that confirms using the Derive feature of what we did. So again, I'll write both of those sort of notations up here of what we're going to do. And then we'll have this one done. So if you've got the older version or the screen type, it looks like Derive of y1 comma x comma x. I mean, not x1 because we had the number 1. And then if you have the other one, it ends up looking like d dx of y1. It'll have a line, and then you put in x equal 1. Okay? And this is a confirmation kind of step, right? This is making sure you did it right. And they do both, in fact, give us a value of 5. Okay, any questions on any of those features? This is not really calculus. We just did that, right? It was just calculator exercise kind of stuff. Okay, let's do something that is, in fact, calculus then. One of your favorites, I remember, from Calc 1 was implicit differentiation, right? Well, of course it was. Okay, well, one of the things that we're going to find out, and one of the things you did know then before, was that there are times when implicit differentiation was simply easier to do because you didn't have as many chain rules or product rules or something like that involved if you used implicit differentiation. The same thing is going to happen with logs. Because of the nature and because of some of the properties of logs, there are times when it's going to be much easier to do a problem with implicit differentiation. So let me give you an example. Here's one that actually has a log in it. And while it is perfectly acceptable for us to simply take the derivative as it is, and this is not a hard one, I mean, it's just x times y, it is a product, x times y, right? And if I do that, I'm going to have a product rule. So if you don't want to have a product rule, you can use a property of logarithms to actually separate the x and the y. Right, and that eliminates us having a product rule, right? So if you don't, you're going to get the same answer. It's just going to take you through the product rule step instead. If you recognize this, the problem will be quicker to do. Okay, so I haven't taken any derivatives. I just rewrote with properties of logs. Now, natural log of x. What's the derivative of that? 1 over x. All right, natural log of y. What's the derivative of that?
1 over y times dy dx.
Oh, you guys are making me smile. You remember the dy dx. Okay, so the natural log of y is 1 over y, but then you have to take the derivative of the inside. That is the derivative of y, which is dy dx. Fantastic. All right, how about the 5x? Good. And the 30? 0. All right, so does anybody remember what you have to do next? Yeah, solve for dy dx, right. So everything that's not actually multiplied by the dy dx, I can simply move with addition or subtraction, in this case subtraction. So I have 1 over y dy dx equals negative 5 minus 1 over x, or the other way around. And then what? We'd be multiplying by y. All right, so we have dy dx equals negative 5y minus y over x. This is fine. There's nothing wrong with how this is written, but what else might be done if you were wanting to do something different, to set something equal to 0 or something like that? What other possible sort of cleanup step might be done? Common denominator. Yeah, if you were to get a common denominator, that might be another way of seeing how this one would be written. There's nothing wrong with the way it's written now, though, so I'm not going to, but that is another possibility. Okay, any questions on that one? Okay. And here is the culmination of why in the world logs and implicit differentiation are so nice to work together. This function, if we take its derivative at face value, is awful, right? It looks like something I'd put on a gateway, doesn't it? It does. It looks terrible. Yet there's no logs in this problem either, right? So you might be thinking, well, but why in the world would I mean, there's no logs. What does it have to do with anything? Well, just because there aren't any logs now doesn't mean there can't be logs put into it. Okay? Just like when you're working on solving an equation or something like that, you can add, subtract, multiply, divide as long as you do it to both sides of a function. You can do the same thing with logarithms. These two values are equal. That is, y on the left is equal to the mess on the right. So it would be the same thing if we took the log of what was on the left and the log of what was on the right. And that will be so nice because all those exponents and radicals and the division and the multiple, it'll all clean up. Okay, so that's what we're going to do. The first thing we're going to do is we're going to take the natural log of y on the left, and we're going to have the natural log of x squared square root 3x minus 2 over x plus 1 squared on the right. Everybody good so far? Okay, so I like logs on the right-hand side because I can change this form. So somebody tell me, actually, why don't you guys take just a second or two and simplify it as much as you can on the right-hand side. You want it in a simplest logs term. So you're going to have you're going to have at least 3 logs here on the right-hand side, depending on how you do the problem. You might have 4. But you're going to have at least 3 logs. You're going to have log of this and log of this and log of this separated with additions or subtractions. So you guys finish filling that out. And then after you do that, I'll write out what I think I have and we'll compare. All right, here's what I think that I would have. I would first have a 2 natural log of x, okay, because the 2 on the x squared can come down. And then I would have addition because the x squared is multiplied by what comes next, and I would have 1/2, the square root's the same thing as a power of 1/2, the natural log of 3x minus 2. Can't separate that. There's nothing that separates the addition and subtraction inside of a log. Minus, because the rest is in the denominator, 2 natural log of x plus 1.
On the half log 3x minus 2. You need an exponent for that?
For the 3x minus 2? Well, originally, the way it was written right here, this does have an exponent. It's 3x minus 2 to the 1/2. And so then we pull the 1/2 to the front of the log. So that is the exponent that was previously there.
So it did not turn to negative 1/2?
No, it's property of logs. Property of logs says that if it is an exponent, it can be rewritten as a coefficient. It doesn't change anything, it just simply moves it completely.
Okay.
I guess you could technically say it still has an exponent of 1, but we never really write exponents of 1. Okay, So, any questions about any of those pieces? Not sure where they came from. All right, we're going to take some logs, or some derivatives of our logs. All right, so what's the derivative on the left? 1 over y dy dx. On the right, what do I have? What's the derivative of 2 ln x? 2 over x, correct. Or 2 times 1 over x if you want to write it that way. All right, my 1/2 is going to stay. What's my derivative of the natural log of 3x minus 2? Not quite. Remember, when we do the logs, we have to put whatever's inside the log as the denominator. So the 3x minus 2 is what should be in the denominator.
1 over 6x minus 1.
Close. We're still missing one piece because the denominator will become 6x minus 4 if we multiply it up. There's still something missing. There's a 3 because the derivative of 3x minus 2, its chain rule, is 3. So I'm going to just change my 1 that's up here at the moment and put a 3 up here. And while it would be okay to multiply the 2 through, I'm going to leave it as a 2 just in case something factors out later that I can eliminate it. It might not, but it might. And then I have minus. Here's a 2 from the 2 ln x plus 1. So this will be 2 over x plus 1. Now technically that's a chain rule as well, but what's the derivative of x plus 1? 1. So I don't really have to worry about that. Okay, that's all the calculus there is. You've done all the calculus. Obviously, there's something else that needs to be done because we're supposed to do, like Steven said before, we're supposed to solve these for dy dx when we're done, and I still have something over on the left-hand side with the dy dx. What do I have? Well, 1 over y. So how am I going to move that? Yes, I'm going to multiply everything on the right by y, but there's a catch. You know what y is. What is it? The mess from the beginning, right? All right, so we've got 2 over x plus 3 over 2 times 3x minus 2 minus 2 over x plus 1. And all of this is times x squared, square root of 3x minus 2 over x plus 1 squared. Yeah, if it were a gateway, you would stop there. I don't do implicit differentiation on gateway, but yeah. The reason this is not going to be okay to leave like it is because you see some repeated things in there that definitely are going to clean up if we do, right? You see the 3x minus 2 in 2 locations. You see the x plus 1 in 2 locations. You see an x squared on top in one place and an x on bottom. Okay, so what do you think the first step might be to doing this? Common denominator for the bracket part, right? Okay, you do not want to distribute this puppy through. That's going to make a mess, okay? We want to get a common denominator for what's in the first set of brackets. So the common denominator is just going to be all 3 pieces that are in the denominator to begin with, right? Because none of them actually have any pieces that match. Okay, I'm going to put this on a new slide, just a moment. Okay, so we're going to end up with the first term is a 2, and that 2 will have to be multiplied by the 2, the 3x minus 2, and the x plus 1, right? The 3, which comes next, will have to be multiplied by the x and the x plus 1. And then the 2 at the end will have to be multiplied by the x, by the 2, and by the 3x minus 2. And all of that is going to be over what? The x, the 2, I'll put it in front, the 3x minus 2, and the x plus 1. And of course, that's not the whole problem. I'm missing this piece right here. And for the sake of what I'm doing, I'm just going to draw an arrow and indicate that it goes there because I'm out of space. Okay? It goes, I actually drew it like going a little bit too low, but it goes right here. That's where that should lie. Let's clean up what we have and see if we can make it better. All right. Oh my goodness. So we have 2 times 2 is 4, 4 times 3 is 12x minus 8. That should be multiplied by x plus 1. I'll come back to that in a second. I have 3x squared plus 3x minus, and we have 2, 4, 4, so that's minus 12x squared, and then plus 8. There it is. I still need to clean up and to simplify what's there. Should there be, oh, an 8x, thank you. Yes, I left that off. I was so worried about the fact that the 8 wasn't showing up to you guys. Sorry, no, you didn't. I promise I didn't either. All right, let's put our piece that we're missing here now. So this over here is x squared square root 3x minus 2 over x plus 1 squared. Okay, a little bit more cleanup and combining like terms. So I have 12x times x, that's 12x squared. But I've got a minus 12x squared later on, don't I? I do. That's kind of friendly. So those are going to go away. I have a 12x times the 1, so that's a 12x. That's going to be left. So let me write these out. I've got 12x squared minus 12x. I'm sorry, not minus, plus 12x. Have minus an 8x and minus an 8 plus 3x squared plus 3x.
Is e going to be a negative 12x squared?
Where did I get this 12x? The outer term's 12x times the 1. First and then outer, inner and last. Is that okay? We're good now? Okay. Nate's not willing to admit it's okay. It's like, no, it's not okay. I don't want to do this at all. We're really close to getting done. Okay, clean up. 12x squareds go away. The negative 8x squared and the positive 8x here go away. What else do we have on the top now? All right, we've got a 3x squared. What else?
12x and a 3x in the bottom.
So that's going to give me, so I first have a 12x squared, right? I'm sorry, 3x squared. And then I have the 12x and the 3x, so we have 15x. And then is it minus 8? Did I miss any pieces? Then my denominator is the 2x, the 3x minus 2, and the x plus 1. And then the question remains, how does that combine or simplify with what remains from the original y that we pulled over from the other side? So let's start with the x squared part of it. What do we have going on there? The original y equation where it says x squared square root of 3x, this one right here. Does it simplify with something? Yeah, it does. It becomes a single just x because it cancels with this x, right? Those are going to simplify. We also have then the square root of 3x minus 2 on top, and we have a 3x minus 2 on bottom. Those do simplify. Do you guys remember how? You're going to have a square root of 3x minus 2 on bottom. It's sort of like reverse rationalizing, right? If you rationalized a square root of x on the bottom, you'd get a square root of x on top with an x on the bottom. The other thing that you can think about is that in terms of exponents, that 3x minus 2 is an exponent of 1/2 on the top, and it's an exponent of 1 on the bottom, and you can subtract the exponents. So we do end up getting, I think I have enough space to write it over here, let's see, the 3x squared plus 15x minus 8 is going to stay. We end up with a 2 on bottom. We have another x on top, right? And we have a square root of 3x minus 2 on bottom. I think we've taken care of these pieces now. So what's left? The x plus 1s. And how are those going to combine? Yeah, x plus 1 to the third. Right? And you could distribute the x through the top if you like. You can get 3x cubed plus 15x squared minus 8x. That'd be fine. But most of the time, that's okay to leave factored form as well. If you were to be doing something else with it, like setting it equal to 0 or something, it would be much friendlier to leave it factored. Any questions on this one? All right.